Well, good morning and welcome to the Mallet Technology webinar series. Happy February to everybody. My name is Boz Marshy. I'm the account manager for Mallet Technology, located in Durham, North Carolina. Today's webinar is going to be, the subject is ANSYS LS-Dyna. It's an explicit dynamics tool. It will be presented by Steve Rugg, our technical services manager. Steve has done the last few webinars. I think everyone knows Steve. We are recording this session, so it will be available on YouTube, and you can go to our website at www.mallet.com if you would like a link to that. The agenda, we'll give a quick overview of Mallet. We'll have the webinar. And then at the end, as always, we'll have time, should have time for some discussion and questions. There is a chat window on the GoToMeeting chat window. Feel free to type questions in there if things come up as we go along. We at Mallet Technology use world-class engineering software tools combined with our broad knowledge and expertise to help our clients compete in today's marketplace and to produce reliable and cost-effective products. We do both sales of ANSYS software, and we also do consulting using ANSYS software. So we can help you in two ways. Quick history of the company. We've been around for helping engineering customers for over 40 years. We started as a consulting arm for Swanson Analysis Systems, which later became ANSYS. It was founded by John Swanson as Swanson Engineering Associates Corporation in the mid-70s. We've been working with ANSYS as a channel partner since 1985. And again, our web address is www.mallet.com. We will have upcoming webinars, same time, 11 a.m. Eastern. Please contact me if you have any suggestions for what topics you'd like to cover. As usual, when we have the next one scheduled, I will send out a invitation to our list. If there's any of your colleagues that aren't on the list, feel free to forward them the invitation or contact me, and I would be happy to add them to the contact list. Again, now I'll turn the program over to Steve, and we can get started on the presentation.
Okay, so thanks everyone for joining. Let me jump to the first slide here. So as always, with any questions, feel free to interrupt and/or submit it in the chat window, and I'll address it either in a moment or if I see it later. So today's presentation, as Boz mentioned, will be on LS-Dyna explicit dynamics. It's going to be a very top-level, basic presentation of LS-Dyna, what it is, how to use it, what is it good for. Really just to kind of, hopefully, if you are not aware of it or only mildly aware of it, it'll give you a better understanding of when it might be useful and potentially if there are problems or challenges in your own organization that it might be able to be leveraged for to help either solve those problems or save money or things like that. So first of all, the first question is, what is explicit analysis? So LS-Dyna inherently is an explicit dynamics tool. So an explicit analysis, it's a method of simulating realistic events that utilizes a different mathematical approach than implicit analysis methods. So the implicit, and I'll talk about this in more detail in a couple slides, but implicit is like the standard ANSYS Mechanical, static structural solver, where essentially you have a large stiffness matrix, and then you solve that stiffness matrix, and then you can calculate deformations and stresses and all your other metrics. Explicit analysis uses a different mathematical approach. So before we do the mathematical approach, what is explicit analysis good for? So there's really a range of things, and And as I kind of walk through what it's good for, keep in mind explicit analysis simulates events in real time, right? So where potentially for static structural analysis, it's not really time related at all. For transient structural, it's mildly time related. Explicit analysis is in real time only. So, right, so it's good for a couple things, right? Complex contact. If you have a lot of contact between bodies, explicit dynamic analyses is great for simulating that. And there's no need, so in implicit world, right, if I have complex contact, oftentimes I have to iterate to a solution. Explicit, there's no iteration required. You immediately calculate the contact properly and then continue on through time. Large deformations, inherently the math allows for large deformations to be calculated easily, same thing, there's no need for iteration. Exotic materials, no need for iteration. Failure, fragmentation, breakup, all these things. Shock waves, explosives, ballistics, these are all things where explicit dynamics is really good. So this event that I'm showing on the screen, this is something that explicit dynamics would simulate true real time. As long as you had all the correct material properties, it would simulate exactly what's occurring. Whether it be this car impact, right? Explicit dynamics is used a lot in the automotive industry to simulate car impacts, to a lot of for safety concerns and safety reasons, airbag deployment. The list really goes on and on. So and I'll show you a number of different examples just to try to help kind of bound what it's good for. And I'll talk about some of the challenges associated with it. Okay, so going to the mathematical fundamentals. So for any type of analysis, we have our basic equation of motion. We have our mass times acceleration plus damping times velocity plus stiffness times displacement is equivalent to force. Whether it's implicit or explicit, this is the equation you're solving. So in the implicit world, we essentially develop one simultaneous solution for the entire global system. And then we iterate to make sure that we're enforcing equilibrium throughout the solve. This scheme is backward looking, so it does not know a future state. So that's what the iteration is needed, right? It guesses a future state, solves it, looks at the residual forces, and then if the residual forces is too high relative to the total force, then it's going to iterate again until it decreases that to an acceptable level where essentially error is minimized. Implicit is unconditionally stable. So essentially, you have to choose a time step that resolves a frequency of interest. Essentially, if you, let's say you're stepping through time in an implicit transient analysis at 0.1 seconds, you're not going to be able to see vibration at 1,000 hertz, right? It's just not going to be available. So you have to choose a time step accordingly. And then implicit also, typically you can step through time in fewer steps. However, each step is much more expensive, right? So there's a trade-off there. In the explicit world, we essentially take all our individual equations, we decouple everything, right? So we end up with many more equations, but the equations are much easier to solve. And with regards to explicit math, it's forward-looking. So based on the past, we can directly predict what the future state is going to be. And then additionally, stability is conditional. So we're required to take a specific time step, right? So in implicit world, we might be able to say, hey, I want to step through time at 0.1 seconds. So I'm going to go 0.1, 0.2, 0.3. In explicit analysis, we're essentially calculating time steps at speeds essentially small enough that we can capture shock wave propagation through a body, right? And shock wave propagation speed is dictated by a few different variables, which I'll touch on. But that's what's called out here, the Courant-Friedrichs-Lewis criterion. And so here, whereas implicit we have few steps, explicit we have many steps, right? So usually explicit, it's not unheard of that you're taking 1 million time steps. You could take many more. It just depends on your problem. Okay, so I'm not going to go too deep into here, and there's a bit of duplication. But so implicit, just to reiterate, so we essentially put together a mass, damping, and stiffness matrices and solve it. And you can imagine if you have, for an equation like this, let's say you have 1,000,000 nodes, this stiffness matrix is going to be 1,000,000 by 1,000,000, and then you're going to have to invert it to solve back for the displacements, right? It's a very labor intensive and computationally intensive approach. Whereas the equation for explicit dynamics, it looks more complicated, but essentially is you essentially end up with many equations that are much easier to solve, right? And so here where you step through time at potentially larger time steps, let's say 0.1 times the lowest frequency of interest, with the explicit analysis, it's dictated by really your element size and material. But a common time step for any of these analyses is anywhere from 1e to the -5th to 1e to the -8th seconds, right? So you can imagine, usually with this type of analysis, you're simulating short-term events. Once you have to start simulating seconds or tens of seconds or hundreds of seconds, it becomes unreasonable in terms of total solve time. However, if I'm progressing at 1e to the -8 seconds, I only have to simulate 5 milliseconds. That's a different matter. So it's just a trade-off, and it also depends on your problem size. Sometimes it may be okay to solve for 30 seconds. It just varies. Okay. So pros and cons of each. And how I would think about implicit, which is think of ANSYS static structural, versus explicit, ANSYS LS-Dyna, is essentially they should be just two different tools in your toolbox, right? They both are very good at specific things, and they both also have drawbacks. So they're both tools for me personally that I want in my toolbox. Every time a job comes in, we always make a decision: are we going to use ANSYS LS-Dyna, or are we going to use ANSYS static structural? It just depends on what you're simulating and what the need is. So pros for implicit analysis: element size has no impact on solution speed, relatively, outside of just element count, right? So for some of our analyses, let's say there's a particular region of interest, let's say there's a stress concentration in a very small fillet, and we need to resolve it, we can just remesh and refine the mesh continually until we get a resolved stress. That's not as easily done explicit analysis, since your time step is dependent on element size. There are ways you can get around this slightly, but it's something you have to really watch out for and be careful of. Another benefit of implicit analysis, so you can simulate long time durations with large time steps, potentially, as long as you're not looking for any high frequency event. It may be more beneficial to go to the implicit world to simulate tens of seconds. The results are very clean, right? So because in the explicit world you are simulating true to time events, you capture all the high frequency vibration. And so there's different ways in which this can become a problem if not properly accounted for, right? It becomes much more important to apply loads in a very smooth manner so you don't get ambient vibration, and the ambient vibration doesn't kind of occlude your response of interest. Let's say you're tracking stress or acceleration or things like this, where I may want to have a very smooth response. I won't have it if that vibration is not properly accounted for. Another benefit of implicit versus explicit is ANSYS's element formulations. They allow for very exact stresses. ANSYS has done a great job over the years developing and optimizing and proving their elements. So essentially you get, I'm not going to say perfect, but you get a very accurate stress response when stresses are of interest. Generally, when I'm working in the explicit world, I'm not as interested in stresses. I'm more interested in bulk deformation? How much plasticity am I getting? Is there any material failure? What's the overall system response? That kind of thing. And so that's not usually a concern, but if I do have to extract stresses, it does become more of a concern because, as I mentioned earlier, refining elements comes with cost. So downsides of implicit. So as many of you probably know, converging simulations with nonlinearities can be challenging, right? It's not always clear why a solution with nonlinearities, whether that be contact, material, or anything else, why it's not converging. There's tools available, but it's not a direct look into exactly what's occurring and how to fix it. And then another con is generally, right, these are generalizations, like an implicit, it's much harder to expand a implicit problem to many, many, many cores, right? Generally, after like 16 cores, you get decreased improvement as you throw more cores at it. Whereas explicit analysis, it's very scalable, up to hundreds, thousands, tens of thousand cores, as long as your problem size is sufficient to support that. Okay, so pros of explicit, and the reasons I choose to use explicit as needed. It does handle nonlinearities incredibly easily without concern, right? So that includes nonlinear contact, nonlinear materials, buckling, etc. Right? This is very easy to handle because it's stepping through time at the shockwave propagation speed or less. Essentially, if you picture two nodes, what it does is, let's say I have two different bodies, and I have a node in each body. At one time step, these bodies are going to be separated. The next time step, this is going to move. This node is going to slightly penetrate the other body. For that one, whatever it might be, millionth of a second, microsecond, that's going to be allowed. The next time step, the solver is going to say, hey, you penetrated me. I'm going to put a restoring force on you, so you're pushed back to the surface, right? So that's why there's no iteration necessary in explicit analysis. Same thing for plasticity, same thing for large deformation. Another benefit is the simulation can be interrogated during the solution. So in implicit world, you generally have to wait until you get the full solve and you get the nonlinear thing to converge before viewing results. A nice benefit of explicit analyses is because it's stepping through time, it's able to output plots at specific time steps as it solves, right? So you don't have to wait. Let's say it's solving for a second. You don't have to wait for that full second to solve. You can say, hey, I want to output every, let's say, 0.01 seconds, right? And then the moment that's output at 0.01 seconds, you can view it and make sure everything's functioning properly. So it does allow for potentially, sometimes, quicker identification of improper behavior in your model. Element failure is handled locally, right? So there's not a huge consideration with implicit from failing an element to the stiffness matrix. In explicit, the element just fails, it's removed. And as I said, problems can be expanded many cores easily. The downsides, right? The time step size, how large a time step can be, it is a large consideration and it is very much impacted by element sizing, right? So what I've found is there are ways to get around it. One method is called mass scaling, which I'm not going to go too much into depth. But if you have important geometry features that are orders of magnitude different in size than the overall geometry, this can oftentimes be hard to simulate, and or it just requires much longer simulation times because you have to have a much smaller time step to capture that behavior properly. And so you're just spending a lot of time churning through these simple equations. So that's one drawback. Simulation sliding can be challenging. The same reason, right? Essentially, if you have sliding between two bodies, I'm going to have one node. Let's say it penetrates through. The next second it restores. It may not restore perfectly back to the surface, so it still penetrates slightly. If this happens over many, many time steps, if the problem's not set up properly, it can penetrate deeper and deeper and deeper, and then potentially invalidate your answer. So that can be challenging. It can also be solved. It's not insolvable, but it's something to consider. And then the final thing is less accurate elements, right? If you are looking for stresses, it's another place where more consideration has to be given to how many elements are required to get accurate stresses. And then as I put more and more elements in and the element size decreases, how do I handle that appropriately with my drawback to time step? Okay. So I keep on talking to time step for explicit dynamics. It's because it's very important. What governs a time step is this CFL criterion, Courant Frederick Louis criterion. So it's really the question of how much time is required for information to travel across an individual element, right? And so essentially the speed of a shock through that material. And so that's governed by, and the true equation is a little more complicated, but essentially the characteristic length of the element divided by the square root of the stiffness of the element divided by the density of the element. So what you can see is, what I'll show you is this is a high-speed video of two slinkies being released. And what you'll see is if we propagate through time at a small enough time step, we can accurately predict the future time because information is only transmitted so quickly. So as you watch this, what's going to happen is they're going to drop the slinky from the top, and they have a high-speed video that they'll show in a sec. And what you'll see is it takes time for the bottom to know that the top was released. And that's where the whole idea of explicit dynamics is acceptable, right? So you can see the top is falling, but the bottom is not moving whatsoever, right? So it's propagating at a very specific time step or wave speed, right? And so as long as we take small enough time steps, we can predict future states. Okay. And then this isn't necessarily an explicit dynamic simulation, but it should give you a sense of kind of how it works. Essentially, you just have nodes interconnected, and rather than a large stiffness matrix, you can kind of just push and pull and adjust things accordingly, and they each respond with their own simple equations. Okay, so that's all explicit dynamics. So the next question is, what is LS-Dyna? What is ANSYS LS-Dyna? So LS-Dyna is a solver that is developed and maintained by Livermore Software Technology Corporation, LSTC. Unlike ANSYS, where ANSYS develops a solver, a preprocessor, and a post-processor, LSTC really only makes, let's say, they don't focus much of their effort at all on pre or post-processing. They're really heavily into only the solver. And I will say a free pre and post processor is available, and I'll show you it later. But it does, particularly for the preprocessor, it lacks features and tools that modern pre and post processors have. So LSTC makes a solver, and ANSYS LS-Dyna is essentially a package that includes a solver, but also includes a ACT module that functions as a preprocessor for the LS-Dyna solver. With that module, you gain all the benefits of ANSYS. ANSYS is pretty robust preprocessor, right? All their meshing tools, all their contact setup, all their material properties. Essentially, your GUI for setting up a problem doesn't dramatically change, but you can still then transition to LS-Dyna. Okay. So real quick, just some simulations and examples, and I'm going to step into the GUI in a second. But these are simulations we've done here at Mallet. This is like a little handheld medical monitor. You can see the internals. Once again, it's real time, so this is occurring over 10 milliseconds. You can see all the different boards bouncing around, impacting each other, vibrating. If you look at the little speaker, you can see how much it vibrates. Once again, because this is a real-time simulation. Obviously, with your naked eye, you may not be able to see, hey, the speaker when it hits the ground vibrates, or you may not be able to see, I get this tremendous amount of deflection with your naked eye. You can capture with a high-speed camera, but with the explicit dynamics, you can simulate it accurately, and then similar to the benefit of just simulation in general, you can interrogate the results endlessly to really figure out whatever problem you're trying to solve and how you might fix it or improve it. And this is just another simulation of a different device we simulated. This is dropping, you can see the impact, and then you can just see the different vibration and potential areas of concern or non-robustness. Okay. So I'm going to come back to this. What I wanted to step into was the ANSYS LS-Dyna ACT module, and just kind of give you a brief overview of how it works and any slight differences that you could expect, things like that. So similar to other ACT modules, right, this is just something that if you purchase it, becomes available, right, and you just turn on, hey, I want the LS-Dyna option available. Then once that's turned on, you get a lower window where you can select Workbench LS-Dyna, and then that'll allow you to open up the mechanical ACT module for LS-Dyna, right? So if I open the module, you're going to see it looks almost identical to like a static structural simulation. The main differences are really, if I click on this Workbench LS-Dyna, you can see I get one additional toolbar that pops up top with different commands that are specific to an LS-Dyna analysis, and or specific commands that allow me to translate my data from the ANSYS world to the LS-Dyna world, right? Because they use two different codes. So the way I would think about the ANSYS LS-Dyna ACT module is it's almost like a Spanish to English dictionary to some extent, right? Essentially, the two are similar enough that you can program it here, and then you say, okay, make my input file for LS-Dyna, and ANSYS is going to translate its ANSYS code to the appropriate LS-Dyna code that you can then run and solve. So the toolbar that I showed above is one difference, and then the other difference you would see is you get a bunch of additional commands that you can input in terms of your model setup that are available when you go to do your normal like insert a force or a displacement or boundary condition. There's just additional commands that allow you to do a variety of things, which I'm not going to go into today because it's too broad. So I'm just going to, it's 11:29. What I'm going to do is I'm going to step through this basic analysis setup. I'll show you results, and then I will show you a couple of examples just to really kind of well capture the breadth of things LS-Dyna can simulate. So what I have here is three essentially identical setups. Each of these bars are moving to the right at 200 meters per second. And then I have three plates. These two are rigid. This is deformable, but all the plates are fixed. The one that's deformable are fixed just along the edge. And then what I also have is this rod has plasticity involved, but no material failure. And this rod has plasticity with material failure at a specified equivalent plastic strain. And it's essentially, these are steel rods, equivalent plastic strain of 50%. But you can see, right, to set up this problem, it's very similar to what I've done before. I have my material properties set up in the standard Workbench material properties. You can see for the model without failure, I still have my plasticity specified. For the model with failure, I just add a failure strain, right? And ANSYS translate that appropriately. And then I go through, I have my connections. I'm going to assign a special connection or a special contact. So I don't need anything here. My materials come in properly. They're assigned according to each body. I have my mesh and some mesh controls. In the way you can oftentimes translate selections to LS-Dyna is via name selections, and then I tell LS-Dyna, hey, this name selection has this ID, right? And then for any manually programmed things, I can call it out accordingly. And so then I have a initial velocity applied at time 0 of 200 meters per second. I have my boundary conditions, so I have fixed edge for the deformable plate, and then fixed bodies for the rigid plates. And then last but not least, I have a contact command that essentially is special for eroding elements, right? If you have element failure specified, this is needed to properly erode the elements and erode the internal elements. If I didn't specify this and I just specified normal contact, I would erode the outer surface elements, but then all the internal elements wouldn't see contact between other bodies. This essentially tells the solver all elements need to see all contact between all bodies. And so that's a really basic setup. I'm going to jump to the LS-Dyna. I could solve this in ANSYS, and then they have their own post processor. But kind of here at MAUD, our very normal order of operations is set up the LS-Dyna problem in ANSYS LS-Dyna, and then solve it, and then come to the LS-Dyna pre-post processor. It's called LS-PrePost. It's a free software package that you can just download online to do the post-processing. So you can see here I have my solved database. Let me get rid of all these windows. And I'm just going to play this, and you can see the different response of the different systems, right? So the left has no material failure. So you can see it just plastically deforms and then rebounds. The right, or the middle, has material failure. So you can see the materials are eroded through time until the energy is arrested, or the energy reaches, kinetic energy reaches 0. And then the right, the plate and the rod have material failure, right? So you can see the plate, as it deforms, it reaches a point where the elements erode, and then it penetrates through the plate and continues on. And so, as you'd expect, right, I can come into this post processor and view any number of things, right? A very obvious one might be plastic strain, right? So if I view plastic strain, I can see, okay, this is my middle one's reaching its failure strain and just eroding. I have some residual strain in my plate that's been bent. I can actually see that I've lost some elements on the front of my rod, and I could step back through time and see when that occurred. So if I step back through time, you can see that it's slowly reassembling itself. I have a full rod at this point in time, and then the next moment I'm starting to get some amount of erosion. And you could look at stresses, you could look at strains, you can look at forces at the interface. I mean, it's really anything you could generally see in ANSYS, you can look at on here. And ANSYS is also doing a great job of developing their own post processor to review it. This is just kind of our standard procedure. And so we've kind of gotten used to it. It's our default. So it's 11:35. So real quick, let me finish up here. So if you decide, so one of the reasons we're often opening things in LS-PrePost versus ANSYS is it's fairly common for us to edit, it's called the K file, edit the input file for LS-Dyna. Not usually dramatically, usually just a couple inputs here and there will change. So what you can do in ANSYS is you click here, you can actually say export a K file or an input file, export to desired location, and it's going to develop the LS-Dyna keyword file, right? And so this keyword file is very similar to ANSYS's own input files. The language is different, but in terms of its purpose, it's the same. It essentially tells the solver, hey, here's my entire model setup, here's where all the nodes are, elements are, here's all the boundary conditions, here's all the material properties, all that good stuff. And it's going to develop this nice long text file showing all that information, right? And you can see my command snippet just was appended on the end. But so if I'm editing it, then I'll usually export it. I can solve it two ways. I can solve it via like a command line, or you can use ANSYS's product launcher tool, just with a couple settings changed to tell ANSYS this is an LS-Dyna run. And once it's done, you can set it up and solve. And now I will say, so the model I solved, this simulation, so this is somewhere, I know this is a very basic simulation, but this is somewhere where it kind of shows how beneficial LS-Dyna can be in given circumstances. So this particular simulation took about a minute to solve on my computer. And you can imagine, and yeah, it's only occurring over 5 milliseconds, but you can imagine in ANSYS Implicit, if I tried to do this in like a transient structural solution, I guarantee you could not solve this problem this quick, because there'd be a number of iterations for every contact, every plasticity. Generally, you can't have more than 15% plastic strain in a given time step. So you have to kind of reduce your time step by that criterion. Where here we're getting failure occurs at 50% strain here, so that would be a concern. So for this particular problem, this is a perfect solution. It's the right tool to choose. And so let me step away from this, and I'm going to touch on a couple more examples, and then I'll talk about kind of the tools and the resources available if you want to try to start working with LS-Dyna or start using it in your day-to-day. So I have a couple of videos I'm going to show. And I will say LS-Dyna is not solely, they do structural dynamics, but they do have other capabilities. You can also do fluids, you can do discrete elements, like discrete bodies like gravel or something like that. And the list honestly is kind of endless about what it can do. The ANSYS ACT module as of today really focuses on the structural aspect of it. But the solver itself can do a great plethora of things. So this, what I'll show you here is this is a different type. I'm just going to kind of go over some other features. So this is called an SPH. This blue, sorry, represents water using SPH elements. In this simulation particularly is looking at the effects of if there's a dam here and the dam broke, what would the response be on this corresponding pillar? So let me play this. So you can see all these elements, dam breaks, you're essentially getting fluid, right? These SPH elements are representing fluid flowing back and forth. And in this particular simulation, they're extracting the force response on the beam over time and comparing it. It was compared to realistic test and found to be very similar. All right, so this is one simulation. Another very common simulation is a car impact, right? This was one of the original purposes for ANSYS LS-Dyna, was to simulate impact in the automotive industry. And you can kind of see that as you look at some of the commands. They have a lot of functionality built in for like airbags and other failure methods that are very specialized in the automotive industry. So here we'll see car impacting at 35 miles an hour, and you can see things buckling, you can see things breaking, you can see things interacting with one another throughout the impact. You can see the airbag deploying, all these things, right? This is where ANSYS LS-Dyna or LS-Dyna itself is great at. It does not struggle to capture these interactions. Another one, this is going to be a forming operation using adaptive meshing. And this one goes fairly quick, so I'll play it a couple times. So you can see it comes down and it's just formed, right? So here you're going to have large deformation, you're going to have thinning of material, you're going to have pretension, you're going to have a lot of different things. So you're going to see here the mesh. This is the original mesh. As it's pushed down, that's the adaptive mesh. You can see it refined dramatically at areas of large deformation. And then you can continue that process in the forming to show, hey, if I trim it, what happens? And then if I release it, what's the sprung back shape? So this is a very common usage for LS-Dyna for manufacturing environments. And then I believe those are all the videos I have. There's many more videos. If it's something you want to investigate, quick Google search, you can find a lot of different videos. And then the last thing I wanted to touch on was just initially at the outset, it can be a little daunting to grasp simulation with LS-Dyna. And so I just wanted to talk about kind of tools available and that you should have available when you're trying to. So the first would be the LS-Dyna manuals. So the LS-Dyna manuals are essentially booklets that dictate, hey, each of my commands is this, and what do they do, right? LS-Dyna still is a little bit in the text-based world, where ANSYS Mechanical APDL was text-based. LS-Dyna is still there, and it's transitioning in ANSYS, particularly ANSYS ACT module, is transitioning it to more the GUI style. But this will tell you kind of, here are all my controls and things that can vary and what they do, right? So the manuals tell you all that. And there's thousands and thousands of these. Generally, you're only going to be using a specific subset, so it's not like you're reading through the whole manual. But it's nice to have on hand when you're making sure that you're setting things up properly. Next is obviously you'd need ANSYS LS-Dyna, right? To some extent, the ANSYS mesher is invaluable. In the ANSYS PrePost free processor, you can do meshing, you can do other things, but it's significantly more challenging and less robust, right? So that's where the ANSYS ACT module comes in terms of allowing the problem to be set up easily and well without significant time investments. And then additionally, there are a number of free resources online that contain a wide variety of tutorials and example problems. So this is a great resource to look at, dissect, and just run through if you're really trying to learn ANSYS LS-Dyna. So that was a whirlwind coverage of kind of explicit dynamics and then LS-Dyna. So let me pause for a second. I don't see any questions in the chat window. Are there any questions about LS-Dyna or what it might be good for, or really anything that anyone thought of? Okay, so I'll leave it as a no. What I will say is, I think prior to my time coming at Mallet, I wasn't really aware of explicit dynamics or explicit dynamic simulations. However, since I've been at Mallet, it's very obvious to me that this is I mean, if we all had all the money in the world, this is a tool I would want in my belt, right? There's no question I'd want ANSYS implicit analysis in my tool belt, but I'd also want ANSYS explicit, right? They're each good at different things and each have their own purpose.
Hey, Steve. Steve,
yep.
I got a question for you. What if somebody doesn't have experience? What if you want to start doing explicit? Let's say somebody just got impressed with this stuff and they want to start. What should they do? What's the path forward in getting access to this technology?
Yeah, I mean, I would say the first and foremost, right, is I would recommend the ANSYS ACT tool, right? Because if you have experience in the implicit world and using that GUI, it's going to set you up well to at least get some basic problems set up. And after that, then that's where I would come back to these resources that I have listed here, right? There's a number of different tutorials. And when I say number, there's maybe 100 different tutorials, right? They kind of walk you through the very basics to the very advanced. And that's where you would be able to grow your knowledge. And then as you're kind of learning, right? If you look online, there's many different like conference papers and different things that put together that kind of give a best practice recommendation for different element formulation, element types, number of elements, where to use certain things, where not to use other things. And so I think the first, ANSYS LS-Dyna, right, because it starts you at something you know with slight changes. And then the second, start looking at these tutorials, start setting up very basic problems that you know the answer to, just to make sure you're understanding things and it's simulating properly, and then go from there. And I should mention as well, that's if you want to do it on all on your own, right? You could also, as Abid has kindly mentioned, do training through Mallet, right? So we are experts in this tool, and we do training, and that should have been more obvious to me to respond initially. But we do training in this. So if you want more of a classroom setting, you can come to us. We can do a class specifically on LS-Dyna. And really, if you have a specific problem that you're trying to simulate, we can do a class where we essentially solve your problem and help you walk through, hey, this is how to solve it, how to set it up, what things to consider as you're solving it, how to interpret the results, all kind of the whole spectrum, right? So yeah, so I'm a little over time, and I think I'm always over time with these webinars. But are there any other questions?
Well, this is Boz, and Steve, I just wanted to add that also, as your anyone who has Mallet as their ANSYS support organization, we can also discuss doing an evaluation of the software if you don't already have it. And I also wanted to say that the two guys in the video shooting the Canon, that is not Steve and I. So I know this is going to be posted on YouTube, so I don't want our insurance company to look at that and raise our rates. So our job is not quite that exciting. We don't shoot cannons and smash cars here in the office.
Digitally. We do it digitally. But, well, okay, everyone. I think that pretty much wraps us up. Yeah, as always, I know Boz can mention this in a second, but if you guys have, I know we're developing these webinars pretty much on a week-by-week basis. If there are specific problems that you want simulated or specific things you run into in your own day-to-day and potentially want expanded or want an answer or guidance, those are always good topics for potential future webinars. So reach out to us, let us know what that may be, and then it's very possible we could put together a webinar specifically on that, because generally if someone has a question on one thing, other people are going to have the same question. So yeah, so thanks for taking the time for listening. Sorry I'm a little over, but yeah, I hope everyone has a good day.
Yeah, thanks everyone for attending. And like I said before, this will be available online, and feel free to give us any suggestions. Everyone have a nice weekend. Thank you.